Good afternoon, good evening, and good morning to all our delegates attending from different parts of the world. Welcome to the fifth plenary session of 7th International Conference on Recent Advances in Geotechnical Earthquake Engineering and Soil Dynamics. In this session, there are two keynote presentations there, which will be delivered by Professor S.K. North and Professor Amir Kenya. And this session will be chaired by Professor J.T. Sahu, my teacher from I.I.T. Delhi, and Dr. Arun Gupta, our good friend from Ministry of Earth Sciences. Before I hand over the session, I would like to briefly present the short bios of Professor J.T. Sahu and Dr. Arun Gupta. Dr. Sahu received his MTech and PhD degrees from IIT Kanpur, India in 1988 and 1994 respectively. He did his postdoctoral research at Institute of Lowland Technology, Japan from 1996 to 1999 and again visited Japan in 2006 to 2007 as visiting professor. Dr. Sahu joined IIT Delhi in 2002 as assistant professor. Presently, he is HAG professor at IIT Delhi. His main research interests are geotechnology for roads and railway tracks, ground improvement, and geosynthetic applications. He has more than 60 papers in reputed journals. He co-edited 6 books and has supervised 52 MTech and 10 PhD theses. He has completed 11 sponsored research projects and more than 100 consultancy projects till date. Dr. Sahu is an editorial member of Transportation Geotechnics Journal, Royal Society Open Science Journal, Indian Geotechnical Journal, and Lowland Technology International Journal. He was chairman of IGS Delhi chapter from 2015 to 2017, and he is a honorary secretary of the Indian Geotechnical Society since 2007. Our co-chair, Dr. Arun Gupta, is presently working as Scientist E in the Ministry of Earth Sciences, New Delhi. Prior to joining the ministry, Dr. Gupta worked at Wadia Institute of Himalayan Research, Himalayan Geology, Dehradun, and Institute of Seismological Research, Gandhinagar. He was actively involved in the setting up of Gujarat's seismic network and multi-parametric geophysical observatories in Kutch region. He worked on seismic wave attenuation characteristics and estimated first-time seismic wave attenuation factor using CODA waves for Saurashtra and mainland Gujarat. Dr. Gupta also taken up research related to earthquake intensity, seismicity analysis, seismic hazard assessment, and site characterization, and brought out very good publications in SCA journals. Since last 8 years, he is playing an important role in the ministry and contributed significantly in coordinating various programs under seismological and geosciences. With this brief introduction, I hand over the session to Professor J.T. Sahu and Dr. Arun Gupta. Please, sir, please take over.
I invite Professor Amir Kenya for the next presentation. And
thank you very much. Thank you.
Dr. Arun Gupta, please.
Yeah. Thank you, sir. So, Professor Amir Kenya is a technical expert in vibration and earthquake engineering at NGI and adjunct professor at Department of Structural Engineering, Norwegian University of Science and Technology. He has received his MSc and PhD degree in structural engineering from Massachusetts Institute of Technology. His area of research and practices include earthquake engineering, soil dynamics, and soil structure interaction. He has published more than 170 papers in peer-reviewed journals and international proceedings and has held numerous keynote lectures worldwide. He has participated in many research projects funded by European Commission, coordinated 3 major projects funded by European Commission, Norwegian Council, and Joint Industry Initiative. In addition, he has led many national and international offshore and onshore industrial initiatives. As a project team for revision of Euro Codes 8, Part 5 of Geotechnical Earthquake Resistant Design. He is also chairman of Norwegian Earthquake Committee for National Standard. So with this brief introduction, I invite Professor Kainia to present his keynote address on high-speed trains with different tracks on layered ground and measures to increase critical speed.
All right, this is the title of my talk, high-speed trains with different tracks on layered ground and measures to increase critical speed. This is going to be a summary of the topics I will talk about. Vibrations generally in railway projects, historical note, what is critical speed, field measurements, some numerical modeling technique, and how to use techniques to reduce vibrations against these on these tracks. Basically, the challenge is that we have now railway challenge coming into urban areas with high-speed line coming closer to congested areas. We could have then soft ground. We could have areas that are prone to vibration requirements, and it could be like high-rise buildings, which actually makes the situation worse. So vibration is becoming actually more and more a serious problem in urban areas. Vibration generally increases due to rail and track and ground irregularity and wheel damage, what we call wheel flat. For the same conditions, vibration increases as the soil gets softer. When we say softer, we mean in terms of stiffness, shear wave velocity, shear modulus. And vibration at the same time increases with train speed. All these are intuitive factors. In many cases, for example, in Scandinavia, very much north of Europe, we have soft soil, so soft that even ordinary high speed when we say like ordinary is like 200 to 250 kilometers per hour, they reach what we call railway velocity in the ground, which leads to a condition as we call critical speed. Loosely speaking, it's like well-known way of saying it among engineers, for which the track and ground vibration dramatically increase. I have a video I will show you. You will see how it works. And in many countries, of course, please realize that when we say high speed, it's easily reaching 400 kilometers per hour. But in many countries with soft soil conditions, areas, even 200 to 250 could be problematic. I have in the written version of this talk, in the proceedings, in the book, some historical note on the problem of moving load. It's like 2D solutions. I have a list and the history of the 2D solutions from many authors with many different techniques, theories, potential theory, Fourier Laplace theory, Helmholtz decomposition, and you name it. Most of the theoretical development were indeed done before 1970s, and a good work by Professor Friba in 1973 nicely sums them up. And then 3D solutions, of course, more naturally are more important. I'm not going through these, and they have evolved over the years, and they are mostly theoretical until, and okay, I will go next pages to numerical. These are all mostly theoretical solutions. And then there are some terminology defined by Cole and Huth. They call it Mach numbers, that it's when you divide the pressure wave velocity and shear wave velocity by the train speed, they are called Mach numbers, Mach velocities for train speed, and you will see why. Now, when we talk about high-speed lane, it is sometimes common. It is common to refer, when the speed is very high, to speak of subseismic, superseismic, and transseismic, borrowing terminology from aero industry, aerospace, and it has to do whether the speed of the train is less than the railway velocity greater than it or greater than the pressure wave velocity. And this image from the pioneering work of Barros and Luco shows what the situation is. The train is moving, this is a simple load on a layered ground. As the load moves in this direction at low speeds, it just wherever the train arrives, there will be a large displacement and then it disappears afterward. As the train speed increases and it's moving still in this direction, then suddenly we see the formation of these Mach lines that represent large displacement in front, like plow lines, bow lines, like a boat on water. That as it moves, it creates these bow lines behind it. Pretty much the same. I have a video soon showing you shortly that it shows. And as the train speeds, still the train is moving in this direction. As it is moving faster, these bow lines actually bend further back and start to make some features also in front of the load, until we even come close to the pressure wave velocity of the region. And then another Mach line is created. So it's a very complicated pattern of displacement is created. Now, while these theoretical solutions were going on and were presented, it was not until 1998 when evidence of this critical speed and large displacement were observed in test runs at a test site in Sweden. Thanks to the work of Swedish Rail Administration, courtesy of them, the site was, because they observed a lot of response at this site as they increased the train speed, which previously did not have any problem. And when they did a good site characterization, it turned out that they found like an organic peat layer with very low shear wave velocity, about 2.5 meters, shear wave velocity of the order of 30 to 40 meters per second. And it's a good combination. They all corroborated and characterized the site. And I show this is going at about 140 kilometers per hour, and the camera is heavily moving. This was digitized after 1998, and then the quality is not as good. So I have a more recent one. This is more recent, like 3-4 years back. And when the train passes, pretty much watch here, because nothing happens until the train comes here. It is slow motion, of course, and you will see wave generated depending on the speed of your receiver. You will see waves generated on the ground. So let's try that. I tried again here, look at here. So basically, this is like a, let's say, animation of the same case. As you see, the train is moving this direction, and these plow lines created as the train moves, and then it creates vibration. What is the critical speed? Main features of the response is that we see a drastic increase in response as critical speed is approached. There is going to be a dynamic amplification. Amplification reduces above critical speed, so that's why it is called critical. Dynamic motions upward and downward happen. At low speed, there is no upward motion, it's only downward. But when you reach this speed, you start to get even the track is vibrating up and down. And plow-shaped wave fronts, called Mach fronts, on the ground surface appear as this move. There are, as I said, I had a summary of theoretical solutions, but more recently, because people want to have all the features of the train track, layering, even non-homogeneity, heterogeneity, everything. So mostly the solutions have been around finite element solution, combination of finite element, boundary element, Green's function solutions. Some people use what we call 2.5D finite element, which means like just a slice of this element and then using Fourier transform in the other direction to make it faster. So these are like examples from the literature with the references underneath them. This is like a full finite element with good boundary conditions. If I'm not wrong, it is abacus, if I'm not wrong. And these are like cases that you get the response by superposing the response from individual loads. And this is the model, the 3D model in COMSOL we tried at NGI through this paper that shows the complete model. It has PML in it so that we do not need to have very large model. This is the section. And this is the section. So a lot has been done recently. And we have another model for filtering, for screening and for capturing the mechanism of like wave propagation in general, that it is based on a track modeled as a beam and on a layered ground. And it is through a kind of a decomposition method that the load interaction between the track and ground is like if it is called P, and then the ground, the response of the ground is expressed through what we call Green's function, which is the displacement at all these points as a result of these loads coming. And then the track model, the track itself by a finite element is straightforward. And then, of course, once you put them together, you get the complete response of the system. So this F is related to the stiffness of the ground and the stiffness of the beam. And this is solved in the time domain. And when we say Green's function, it's like the solution at all these points due to a unit load. And it's usually, you know, there are analytical solutions for them that are solved numerically by time integration numerically. So we used that one when we were involved in this research project, and this shows some of the simulations and some of the measurement. What you see here is like the red is the measured values. This is like at one point of time, consider it that you freeze time and you take a photo of the displacement pattern. So this is like the train location. These are like the axle loads, and you will see that the displacement is as expected. It is like the footprint of the loads. So everything is like positive downward or negative downward. And the simulation in blue is pretty much nicely matching it. Everything is, of course, downward. But as the train speed increases 185, you will see the pattern completely changes. It's not like wherever the load is, like the displacement is maximum. And then we look at that moment of time, the displacement along the track is pretty complicated. It's upward, downward, it has a vibration pattern in it. And of course, we did not have the result for critical speed because they could not do the test. So these two are only the result of simulation. So if we plot all these data on a graph with train speed on the horizontal axis, as the train speed is low, let's say even up to 100 km/h, this is the curve for upward displacement of the track, and this is for the downward. Basically, there is practically zero upward. It's all vertically moving downward. And there is like a lot of like up to 4 mm in this case. And as the train speed increases, you will see that not only this one increases the downward, even we start to get upward displacement. This is the feature I explained to you. And there is a point that we loosely call critical speed when the maximum displacement is achieved. More theoretical solutions have done it mathematically by presenting critical speed in terms of group velocity of the continuum, like several researchers have done. The most recent is by Professor Hausel of MIT, and very nicely presenting this critical speed in a mathematical sense. But for engineering purposes, this is easier to visualize, that the point where the maximum displacement is observed. And just to be sure, this COMSOL model is doing this a good job. This is modeled from the top. The load is moving along this direction. You will see these are the colors of the displacement. These are the Mach lines. generated like this as the load is moving. And this is like a 3D pattern. As you could see, displacements penetrate into the ground, same fashion, and also as the load is moving on the two sides. This part is like the PML, so that the model is actually pretty small. It's only this part, and everything around it is like this absorbing PML, so-called PML model. Now, having said all this background, what do we do? How do we deal with? Now we could have vibration problem. How do we deal with it? So there are different ways. One is at the source, under the source. Somehow we should fix it here. The other solution is that we stop it on the propagation path. And then the other thing is at the receiving point, either in the building by making it stiffer, whatever, or like in the foundation, for example, making it stiffer, putting piles, again, whatever solutions. So there are different ways of dealing with these vibrations, and they depend on the type of vibration. Basically, there are two regimes when it comes to ground vibration from trains. One is usually at high frequency, and they are these high frequencies. When I say high frequencies, like over 20 hertz, 25 hertz, pretty high frequency. They are usually created due to rail or wheel unevenness, corrugation, being defected wheel, or cracks, flats. So these are usually at, or the track being not perfect. So these are usually handled often by 2D models. This is a 2D model. The load is perpendicular to the plane. And this is if there is, like at a given frequency, I'm just showing it qualitatively, one case just, and it shows the ground vibration from, I forgot exactly what frequency, 20 hertz or something, what pattern we have. And then this is like after putting some countermeasures, like in form of trenches or stiffened ground. And you will see what it does in this case is that it returns the vibration, basically reflects them back. And this area, which is mostly for residential and other purposes, is protected. So this is one type of countermeasure, which works for usually higher frequency. But when we come to critical speed issue, which is a problem that it's created basically at the source, and basically putting such things, it doesn't help, because this is lower frequency and these measures usually are very ineffective. So and also one has to do something with the track, otherwise the track will be in trouble. So there are like how to deal with them, and these are like happening many places. The most recent of them, you see the project HS2 in UK, in some areas has to deal with it, for example. There are different solutions. One of them is actually ground stiffening, let's call it, or ground improvement. One of them very popular in Northern Europe is through lime cement column, which is like mixing the ground with cement as it is extracted soil, and then you basically at the end make a series of stiffer soil, half concrete, and make the ground stronger. It's very, very fast operation and rather cheap actually. So this was tried at this site that I showed the video to you that had this problem. It was performed at that one. It was 2 lines, so 1 line was removed, only 1 line was used, and then during that time it was applied, this technique, as you could see how it looks in some, and it was penetrated through that peat layer, and some of these columns were driven further down, and it turned out to be very effective. The red is like the displacement along that as the train was passing. You could see like large displacement, like over 1 centimeter. And after, this is before and after this countermeasure, it was dramatically reduced to almost nothing. So it was pretty much effective. And we did simulation of it in COMSOL as well. I'm not going to show you, but I'll show other type of results. Now, the question is back to the same thing, the issue of critical speed, how to increase it. Because the best way, the only way to avoid the problem is like, it's not like having trench next to the track or something. You need to do something at the track, and the solution is basically to do something so that this critical speed is increased, so that we are not getting to this area, basically pushing this to the right. And how to do it? In my paper, I have investigated 3 methods, 3 cases I have considered. The first case is stiffening the ground. Okay, this is this one. It's the opposite order. The first one is the second one. Let's say stiffening the track and embankment, like putting a stiffer embankment, or even putting a very stiff beam underneath the track ballast and all that, and making it stiffer, which intuitively makes sense. And as the train goes, it just distributes the load better. The second one is stiffening of the ground. So rather simply replace a part of the ground by some improved material, by some better material like crushed stone, or injection and grouting. There are many techniques, soil improvement basically, or use of piles. So basically put the track, whatever it is, a beam or whatever, on a series of piles. It could be one pile, it could be several piles, but anyway, in the area, because this problem is not necessarily everywhere, it's like certain stretches, and then it could be done this way. Pile driving is simple, so this could be done rather easily, and it's very reliable, because then you are sending all the loads to deeper layer rather than being worried about gradual settlement, effect on. So each of them have advantages. Now, to measure the performance of these methods, I first look at my base case, which is no measure, which is the case I showed through the video. And it is the site with this organic layer, soft soil. These are the train loads, exactly as was used in the test runs. And these set of figures are displacements. And these are the corresponding, so they are the same information. Ground velocity on the track, particle velocity, and this is displacement. You just need to think about this one. These are different speeds. This is time. So as the train passes, and we look at a given point as the train passes, so when the load comes, this pattern of displacement is observed at a given point as a function of time. So this is at low speed. So this is as we expect, low speed. But as the speed increases, the pattern starts to change, and then completely changes, goes to this superseismic and transseismic and others, like track moving upward and the vibration. And numbers are dramatically larger. This is like below 1 centimeter. This is already over 2 centimeters. So this is what I call as base case, as the case was there, because we have numbers for it, we have data for it. So the first case is stiffening of the ground. This is ground improvement. So what I did is that I replaced, this is a very effective method and could be reasonably done. It could be different ways. As I said, it could be injection, grouting, or it could be replacing of the material. So, and in this case, I replaced it. The peat layer was completely replaced. That's the problematic layer, natural. So this was what was done. And this is like the base case. I just copied it here for reference. And same velocities. And now with the new track, let's say track is the same, it's just the ground is changed. You will see that, please note that it's not the same scale, by the way. If I use the same scale, these figures would be very small. So this is like much smaller. For the same speed, displacement is considerably smaller. Look at this one is 0.003 and this one is 7-8 times. So definitely it is a very effective technique. Of course, in each case, as you increase the speed, vibration displacement and vibration acceleration speed increase. But if we use that one as a measure, it is an effective technique. And of course, then one could go ahead and optimize. If you have a good technique, like the tool I showed, VipTrain, you could easily optimize it, like how much, because we don't want to make it too stiff. Too stiff has its own problems, actually. It has problems for higher frequencies. So there's a balance, how much we want to make it stiff So yeah, so this was a very effective solution, and it's very reliable. Just to get an idea, because from this figure we see that we are not getting anything close to critical speed of the new system. So that means that we have succeeded in increasing the critical speed, because it's nothing happened. So what is, if we want to see what has happened with the critical speed of the new system, so what I did is that I basically increased the train speed, and I computed the ground displacement as a function of train speed maximum. And we will see that, you know, as the train speed increases, there in those simulations, I stopped at 300 kilometers, but you see that you increase at about 450 kilometers per hour, you get the maximum response. And then after that, again, it reduces. This is what could be loosely said as critical speed of the new system. And we are, of course, if the speed is design speed is like about 40% lower than that, like in this range, it's a success. It's a good solution. We're way away from it. So this is that one. But then the other solution was track stiffening, because people could say, well, this is easier. We just simply make a stiffer embankment on the ground. We don't need to touch the ground, or maybe even put a girder beam, a stiff beam underneath the ballast and make it stiffer. In other words, the track is stiffer. So again, I'm showing only two speeds. For example, use of stiff beam. I'm showing just two cases. One is the base case. This is the same before, the two speeds, and stiffened track. When I say stiffened track, I mean the results for stiffened track are when stiffness of the embankment or the beam together is in the base case is quadrupled, so 4 times. So 4 times. So we see an improvement. It's the same scale in this case. So we see an improvement. However, when I see this upward movement, there is a good improvement. But when I see this thing, it gives me a bad feeling that maybe I have not fixed the critical issue. So it has helped, not dramatically. Stiffer track reduces the displacement and vibration, fine, but they do not noticeably change the critical speed, which I'm going shortly to tell you, because I see this feature of this upward movement. Displacement reduced is not necessary. And how can we judge it? If I look at ground response 10 meters from the track, away, track side vibration. Now, this is the original track. So I get like typically, let's say 4 millimeter. Yeah, but you see this feature? It's really vibrating because of this Mach lines and plow lines, you know, moving. So it does vibration. And when I look at the case, the same for stiffened track, it is reduced, fine, but we see all these vibrations again. So first of all, the amount of reduction is not dramatically, whereas the previous solution was factor of, I don't know, 10, 7. Here is just maybe 20, 30%, and it is vibrating. And we should realize that this is not good, because if this is in an urban area, the houses around start to feel this. So even if the level of displacement of the track is okay, this is not at all a pleasant solution. Finally, the solution of piled track. If I put the same track on a beam and the beams are on a pile, so in this case I chose just arbitrarily, just to get a feeling, 2-meter diameter piles, concrete piles, 9 meter long, so that they penetrate through that soft layer and then a little bit to the good layer, and installed at every 12 meters. It's arbitrary just to get the picture. And this is again the base case. And this is like, again, same speeds, but with the vibrations on the track of this case with pile track. And you see it's not the same scale. Vibrations are dramatically reduced. Now this one, for example, at the critical speed, which is the issue, is dramatically reduced. Again, look at it. I mean, it has vibrations, but it's dramatic. So it is a very effective solution. It works very well. What I'm not showing here is that, and it is in the written paper version, is that vibrations can be reduced dramatically at close to the piles, where the piles are. And But resonance of the beam between the piles could cause large vibration at mid-span. This is not a critical speed issue. It's because the beam in between could go into dynamic resonance. So a design optimization is required. Maybe a stiffer beam, maybe closer piles, for example, smaller piles but closer, that sort of thing. But at least it is a very effective solution. It has the advantage, extra advantage, that you pass on the load to deeper area that has less settlement. So it is in a way a good longer term solution. And that brings me to the summary that there are basically two response regimes when considering reduction of ground vibration from high-speed train. I said these two regimes are high frequencies, basically has to do with irregularities of the train, of the track or the wheel that causes higher frequencies. And then we have, for that one, there are other solutions. That's not the topic of this discussion. But then it is below the critical speed, which was the focus of this talk. It is high frequency. Yeah, below high frequency, then we could reduce those high frequency response. But for this critical speed, yeah, this is the one I'm trying to say. These two are basically the same thing. We are still below critical speed, but it is high frequency is the issue. If the train speed is close to the critical speed, the only solution then, it's not like trenches or other thing, is that we should reduce the response. To reduce it is to increase the critical speed itself by ground improvement like stiffening it or use of piles, but not by track stiffening, not just putting like a stiff beam on the track on the ground. So it has to be something inside the ground to change the characteristics of the propagation medium. And track stiffening will reduce the track vibrations, but the vibrations away from the track, like trackside, are not noticeably affected. And it is important for design of tracks on soft soil through urban areas, because now residential areas or sensitive facilities come very close to the track. So even if you reduce a little bit of the track vibration, the vibration is there to the surrounding. And then that brings me to the acknowledgement. I have to thank many projects that have contributed that this has resulted in this presentation. European Commission project SuperTrack, Swedish Railway Administration project, through several projects that continued after those test runs. I should thank them. Again, the recent European Commission Horizon 20 financial project, Destination Range. Many colleagues at NGI, I just mention a few: Karin, Noren Koskrif, Christian Matsus, Junsan Park, and Jörgen Johansson for collaboration through these projects and giving various input. And I think at the end, I would like to thank the organizers of this conference for inviting me for this talk. And in particular, Dr. Ravi Jacob, because he has been my direct contact all along and has been patient. And of course, the conference team that has done a fantastic job for being very organized and making it easy for us presenters. Thank you very much for your attention.
Thank you, Professor Kenya, for your very informative and knowledgeable presentation. So, as I understand from your presentation, that operating or critical speed is more like our resonance in the dynamic system. Yeah. So usually we have designs which are based on strains, displacement, or stresses. So when your trains reach the critical speed, then your displacement increase disproportionately, and
Yes.
that lead to accidents or problems in the passenger comfort, etc., and the neighboring structure. The only thing missing was how this VS can be incorporated in real design. That aspect could be a further development in this field. So with that, I will look at the, there is one question presently. Actually, you have already answered a lot of questions, so I don't have to speak many questions, but the question is from Mr. Harsha. He says how the soft ground can be treated. How the soft ground can be treated when excess pore pressure changes abruptly due to train dynamic load vibration.
Yeah, that's a good question.
This excess pore pressure over time results in huge settlement and more maintenance costs. Is PVD helpful in this scenario?
Yes, no, it's a very good question. Realize that at the end of the day, we have to make sure it's not like earthquake. We have to make sure that the ground vibrations are reduced. We are not going to allow trains go at critical speed. So basically, requirements today are to avoid it by 40%, like 60% maximum. So once we get to that point, then we have avoided critical speed. I mean, otherwise the track will be damaged, deteriorated quickly. So once we avoid that, then that means that the vibrations, and as I explained, the vibrations will be reduced. Then it's correspondingly the strains and the other things will be so much reduced that the pore pressure buildup will be very much diminished. So the chance for pore pressure buildup will be, it's not earthquake. The strains are not at the level that it brings the pore pressure. And even if there is a special soil that for some reason could be doing that, then one should do other solutions like drainage or other systems, so that, because I think once you avoid these things, you do not hit this problem of pore pressure generation. If at all a case exists, then one has to find replacement like sand drains, like the solutions that we have in earthquake engineering, so that the pore pressure, if it is generated, dissipates quickly.
So just I was wondering that the tracks in European tracks, most of the this high-speed tracks like your the TVG and other tracks, they are mostly on the ballasted track or on the concrete tracks. Which type is mostly used? And
yeah,
the proportion.
Yeah. No, I don't have exact percentage between them. The dominant one is still ballast track.
Ballast.
But then, of course, ballastless, like slab track, we call them slab track, are being experimented and being used. We have it in Germany, we have it in the Netherlands and other countries, and depending on stretches, they are being tried. Ballasted track are the most convenient in terms of repair, because gradually when there is settlement and other things, they could go there and tamp it so that you get back the flat aligned ray. So that's why it is preferred. But of course, yeah, I don't have exact, my gut feeling would be factor of, I don't know, 20% to 80% between the two. It's just a gut feeling.
And any advantage of the flexibility of the track also, because ballasted tracks are flexible compared to slab track. So
yes.
any advantage in terms of wear and tear of the
Yeah, that is actually another good point. As I said somewhere in my talk, if you make the track, of course, these slab tracks are not very stiff. They are not very stiff. But anyway, just to give you an idea, when you make the track too stiff, then you bring in high frequencies and there is more problem for fatigue damage. So that's like the wear that you mentioned. So that these are like all these elements in play that one is maybe still preferred over the other one. Of course, the slab track has the advantage that it evens out the stress distribution, especially for soft ground, and it is easier to construct. It's like these slabs are installed. So it has to do with also the supplier chain and the what system has more, like, let's say the construction industry is more prepared for it, has better experience, the prices and all that. But anyway, as such, it's not like slab or ballast is chosen because it is a better solution for wear and that sort of thing. It is like many other factors. But as I said,
So when you are saying fatigue damage, it is with respect to the second regime, that is the unevenness of the track, isn't it?
Yes, correct.
Okay.
Correct. Yes.
Thank
Because
you
if it
so
is a
much.
perfect, if
Yeah,
it is a
please.
perfect track, nothing happens. There is one question, if you want me to answer, how can you
Yeah.
identify resonance during numerical modeling? Well, I don't want to call it resonance. It is actually a wave propagation phenomenon. When the speed gets to a point, it looks like resonance. It's not really. So numerical modeling, the easiest way is when you do finite element, for example. You can, if the finite element is robust, good model, you can increase the train speed and run for different speed. You will see that gradually as you increase, your response also increases. It is a very engineering good approach. And at one point you see that, oh, it comes to a peak, and then after that, and then you will see at the same time, track is definitely together, it's going up and down. And so this is like, if you call it, the term is resonance, if you want to call it, this is the way in numerical modeling you can identify how far you have come or are you away from it.
The only thing is here you cannot operate on the other side of the peak, other side of the critical speed. Like in
yes,
you can operate on the other side of the regional,
yes,
but here
yes,
you have to be on the one side only.
yes, absolutely.
So thank you very much, Professor
You're
King.
very welcome.
Been very informative and very nice presentation.
You're very welcome.
Thank you so much.
My pleasure.
So with that, I hand over to Professor Ravi Jakka.
Thank you, sir. On behalf of organizing committee, I thank our esteemed speakers, Professor S.K. Nath and Professor Amir Kenya. I must tell you my brief interactions with them. It's a really wonderful experience to work with both of them. And Professor S.K. Nath is always used to be very prompt in responding. And he's the first one to respond to my mails, proofreading, or whatever. And we all have seen his energetic presentation. And the same thing, in every aspect, he's so energetic. And though he's a topmost researcher in India, but he is down to earth man. He speaks so nicely and so politely, even with me, like juniors like me. So thank you, sir. I really enjoyed my interactions with you. I'm very grateful to you, sir. And
thank you very much.
Thank you, sir. And my experience and interactions with Professor Amir Kenya started even before this conference, maybe 10 years back. And he is very friendly with particularly Roorkee and I.I.Sc, Indian Society of Earthquake Technology. He is supportive of all the activities of I.I.Sc. Even now, when we requested him to deliver a keynote, he immediately accepted. And in fact, he is in the middle of his vacation. He took break from his vacation for the delivering this lecture. Thank you, Professor Amir Kenya. Thank you very much.
You're welcome.
Thank you very much, Professor Ravi, for everything. And you had been really great. And you have been very patient. And I think our collaboration for the whole of the conference went very well. And we have developed a very good relationship among ourselves. That's very important. Thank you. Thank you very much. And I hope that you prosper and you do well. And in future also, I think we retain this relationship and we go ahead with this, because IIT Roorkee is one of the greatest institutions and doing fantastic in geotechnical earthquake engineering. And this is, I think, one not all like others. So therefore, with this, I again thank the organizing committee. Thank you all very much for this opportunity. Thank you. All my best.
Thank you, sir. Thank you for your well wishes.
God bless you. God bless you. And your daughter is also a very nice performing artist. So therefore, please encourage her, and we in future would like to see her live. Thank you.
Thank you.
Thank you very much. God
Thank you,
bless
sir.
you, your family, everybody, and all my colleagues, Professor Shitaram, Professor Maheshwari, everybody, all the colleagues and all your team members. Thank you. God bless you all. Okay.
Thank you, sir.
Bye.
Thank you very much. Because of all of your cooperation, and we members of organizing committee are able to do well this conference, sir. And we also very much thankful to our chair, Professor J.T. Sahu and Dr. Arun Gupta, for kindly accepting our invitation and chairing this session. Thank you,
You
one
are
and all.
welcome. You are welcome.
Thank you.
Thank you.
And before we wind up this session, we have few announcements. One is regarding the exhibition hall. We request all our delegates to visit exhibition hall. There are a number of stalls and they are very informative, and they will tell you about latest happenings in the field of geotechnical earthquake engineering, and also provide you information about various societies and various other activities. Please, all of you, please do visit. And that exhibition hall responsibilities are taken care by our Dr. Parthasarathi. He is the vice chairman of this conference. He is here. Sir, would you like to add anything, Dr. Sarathi?
Thank you, Raviji. I think there are many stalls. Exhibitors have come to participate in this program. So all the participants are requested to visit each and every stall. So to know more about the products and services they are offering. There are some professional bodies like TFI, IGS, and I.I.Sc. So you can download some brochures and get more information of the upcoming programs. There are some companies who manufacture drilling rigs from US, from India, and there are some companies who manufacture testing equipments, and there are companies who sell softwares. Particularly, you can get to know about the latest software that is available for the application geotechnical and civil engineering. So kindly I request all the participants to visit the exhibition stall and encourage the exhibitors so that they also feel overwhelmed with your participations. So with more of technical feast, even that is also part of our conference. So kindly I request that please visit the exhibitors. Thank you.
Thank you.
Thank you, Dr. Parthasarathi. And I also request all our participants to visit networking launch, where you can interact one-to-one with experts live using video chat and text chat, and also visit our e-resource corner, where you can get all the information, the presentations shared by our speakers, and also the manuscripts and keynote papers, everything are available through e-resource corner. With this, we are closing this session, and the next session will be starting at 4 p.m. onwards in parallel halls. You are all requested to join us at parallel halls. Thank you, one and all.
Thank you. Thank you.
Thank you.
Bye.
Thank you.
Bye.
Thank you.
God bless you. Okay. Bye. Take care.
Okay.